last time, this is what we did. So, we were talking about, of course, force, vibration, damped systems, right? The case of harmonic excitation, right? Harmonic loading. So I believe what we did last time, we derived or we set up the equation of motion, and all the way we went to do the frequency response function, right? So we basically, the last topic we covered was frequency response function, which we said in the case of undamped systems, it was h of r, 1 minus 1 r squared, which basically we plot the absolute value of that. In the case of damped systems, that is a system that is subjected to a harmonic excitation of this form, okay? In this case, the complex frequency response function is like this. Or the magnitude of that which we plotted, in other words, this is what we plotted, was 1 over 1 minus r squared plus 4 zeta squared r squared. So we plotted that, I believe I did discuss all the details as far as what happens and why the response as the damping increases, the peak shifts to the left of r is equal to 1, and of course up until the point that we get to damping ratio of zeta 0.707. So these are all for the case of damping less than 0.707, shifts to the left, and beyond that, of course, then all the curves are below this static level, or static displacement level, for damping ratio of 0.007 or larger. The dynamic response is always less than, the maximum the maximum dynamic response is always less than the corresponding static response. I think we derived that, right? Their equation and so on. So we really want to show the application through some examples and whatnot of harmonically loaded, harmonically excited systems. And one of the most interesting application of this case, okay, is not just that, okay, we have an ideal situation, you have a harmonic load on the system and so on, but is more than that. So before doing that, before getting into some of the important applications, let me do one example problem here, which I have prepared for you, and then we'll discuss other applications. So let me do an example. Let's assume that we have, say, a building, and this building is like this. Okay, it's not fixed, it's hinged to the floor. It's not, it may be a building, or can be actually some kind of a raised floor, or some some kind of a system or a foundation that supports a rotating machinery. So what we have here, this is supporting a rotating machinery. I will show it like this. Some rotating machinery, okay? This rotating machinery, okay, exerts a force that looks like this. Fz is 200 sine of 5.3 T pounds, okay? Let's assume the damping ratio of this system is 5% for this structure. And what we want to do, so in other words, we assume that this rotating machinery, as it is vibrating, it is exerting a force like this to this, causes a vibration like this, okay? And what we want to find out is the steady state amplitude, or the maximum, actually, steady state, I better say maximum instead of steady state. Amplitude physically makes more sense saying that maximum steady state displacement. Okay, that's the first thing we want to find. And then we want to find the maximum dynamic bending stress. In other words, we want to build a foundation or some support mechanism to hold this rotating machinery, and we want to basically, knowing that, say, this is made of some materials, which I'll give you of the details, how much would be the maximum of the stress that develops in these beams. So we can find out if you put this machine on top of this, will be safe, okay? So for going to the strength of material, for something like this, each K is 3 EI over L cubed. And the I and so on are given. In fact, let's see. Yeah, E and I guess, were given in a different problem, so that's okay. So for each of these is K, so for the total, obviously the total are going to be parallel, so the total would be 2 times 3 EI over L cubed. These parameters are given. E is given as 30 times 10 to the 6 PSI. I is given as 69.2. I is given 69.2. Okay, yeah, that's right. Inches to the 4, and length of this beam is given as 15 feet. Okay. So if we substitute in here, K would be, okay, 2 times 30 times 10 to the 6 PSI, okay, times I 69.2 divided by 12 times 15 cubed. That will give us 2,136 pounds per inch. So this is total K for the system. Yes?
Are you missing a 3 times on top there?
Which one?
Or it's 2 times 3 times 3.
Oh, this one?
Yeah, it's 2 times 3 times
Oh,
30.
times 3, I'm sorry. 2 times 3. So that would be okay. So this is the display, stiffness. So the equivalent static displacement, which, okay, I call that AST, okay, was what? F0 over K. So we have F0, okay, which is 200. So it would be 200 over this K, which is 2,136. So the equivalent stiffness, the equivalent static displacement would be 0.936 inches. So that's the static displacement, okay? So we want to find a maximum steady state displacement. So as we know, the maximum static displacement is what? U max is basically that the maximum value of frequency response function times this AST, right? Because that was what it was, right? F0 over K, 1 minus R squared plus 2 zeta R squared, right? So this is what? This is the maximum, or this is the amplitude of the steady state response, which is a maximum value of the dynamic displacement, right? That's what it is. So let's just substitute for those. The frequency of the forcing function you're given, we need to also find a damping ratio. The mass is also given. I'm just giving these to you in pieces. Mass is given as 15,000. Somehow there's, yeah, 15,000. So natural frequency then would be K, which was 2,136, divided by M over 15,000 over 386. That will give me the natural frequency of 7.41 radians per second. Yes?
What are the units on the mass?
Usually pound mass. That's why we're converting it to slugs. Okay. Okay. So, so that's the natural frequency. We have the forcing frequency is given as 5.3. So R would be, okay, R, which is omega over omega n, would be 5.3 divided by 7.41 is 0.715. So it's good to at least, when you get to this point, visualize or go back to sort of the plots that you have, okay? Damping ratio is 5%. So you must be in this region, right? Because below 0.707, you're here. So the frequency response function is actually something like this for this case. It would be something like this. And obviously, R is this, so you're somewhere here. If this is 1, you're somewhere here. So, and of course, the peak shifts to the left, so you have something like this, okay? So you can, before solving the problem, you can imagine, since you are right here, right? You're right here. This is your maximum U. You see that your maximum dynamic displacement, because of the damping being less than 0.707, is definitely going to be higher than the corresponding static displacement, okay? So before even solving for that, you could see that. But nevertheless, let's find out the maximum value, okay? the maximum value, okay, we'll just substitute in here. We have this one, 0.0936, which is F0 over K, divided by 1 minus 0.715, okay, square of that, plus 2 times zeta, which is 0.05 times R value, which is 0.715, square of that, the square root of the whole thing, right? That's basically this as an expression. Okay. So if you calculate that, I don't want to do a messy job. So let's go back here. Okay. Because we need more space. Oops. Okay. I'm not going to erase that because we need this figure. Yes.
The U max there, is that defined as the peak value
Exactly.
of that curve?
That's right. It's the peak value, which is this.
But that's at that specific R, which might not necessarily be at the peak, right?
Oh, this is at this point, right? Which is at whatever the R is, right? Oh, you mean,
Like,
no,
couldn't
the
the
R,
R
the
percentage?
peak is towards the left of 1, but that's where the peak value for this is. In other words, this is the R 0.715, right? We know that a peak is always shifts to the left of R equals to 1. Is that what you're asking?
Isn't it possible that our R is between where that peak is and where the line for 1 is?
Oh, no. R is, you mean for the R value, okay, this is the, oh, I see what you mean. You mean, what you're saying is that, okay, let me actually do that in here. So what you're saying is this. If I plot this curve, and this is 1, it looks like something like this, right? So what you're saying is, how do I know if the R value, right, is right here, right? That's what you're saying, okay? R value of 0.715, right? That's what you're saying, right? This R value, right, is just a ratio of the frequency. So you're right, it may not be exactly at that, you're right. I don't know where it is, and I don't care, we don't need it. All I need is just this value. That's a good point, yes.
Okay, so the U max is where the R intersects the curve, not necessarily.
Right, that's right. Yes, no, you're right. That's correct. So, but I don't need that anywhere. All I need is just a maximum value. So if you find a maximum value, you see that U max comes out to be, okay, 0.189 inches. So you have, by looking at this qualitative shape of the plot, you can see that you have confirmed that the maximum displacement is larger than the dynamic, static, corresponding static displacement, almost twice of that, right? So I should have done a better job here in something like this. Maybe if this is 1. Okay, so, but this is the maximum displacement, right? What that means, the force acting this way is causing basically this displacement in this beam, right? What is that force? That force, right? If you look at, you have a beam like this, right? This is the force, or this is the maximum force causing it, right? If you draw the free body diagram of this beam, right? You have only a force at the tip, that's where it is acting, right? That means this is the shear force in the beam, right? That's the shear force in the beam. So this force, which is basically K, in other words, the force that you're looking for, okay, if this is the one that causes this displacement, and this is K, okay, and that's the maximum force, so that force, max, which is the shear max in the beam, is what? K times U max, right? So you have the stiffness, you just multiply that by that, you will get V max then, or the shear force maximum, would be basically whatever that was, 3EI over L cubed, right, times this U max, and that will come out to be 201.8 pounds. Okay? So you have a beam with a constant shear, remember from strength of material, right? How do you find the maximum bending stress? You need to find the maximum bending moment, right? So if you have a constant shear, moment is the integral of that, or in other words, it is equal to the total area under the shear diagram. So the moment, maximum moment, right, would be that V max times L of the beam, right? Remember from strength of material, this is the shear force, right? You want to plot the moment diagram, right? It's just that shows this is the slope of this curve, which is constant. This was pinned at this point, so moment here is 0. So the maximum moment, which is this, is the total area under this diagram, right? So that's the moment, which comes out to be K V max, okay, would be 36, comes out to be, if you multiply it out, 36, 324 pound inch. Length was 15 foot times 12 inches. So that's that. So you remember now the okay, was the thickness is given, okay? The I over C of the beam is the section modulus. So maximum moment is what? You remember was M Y over I. So if you had a beam with this cross section, okay, this was basically Y over 2. But anyway, in this case, of course, unfortunately, the problem has just given the value for that. So we call that, you remember in strength of material, this one was called C, the distance from the center of this cross section, or the centroidal line or neutral axis, to the top or top fiber. If it was symmetric, it doesn't matter, top fiber or bottom fiber, but to the extreme fiber, which is where the maximum bending stress occurs. And we call this C, or we show that at M over I over C. This was called section modulus. So you go, in the problem, actually, this is an I-beam, section modulus is given at 17, which they give it to you, so divide that by 17, you get the maximum stress, bending stress comes out to be 2,136 PSI. Then you look at, of course, what is the ultimate stress of, if it's a steel or whatever, if that exceeds that or not. But that's the maximum bending stress that you get, which in this case, given that the displacement was almost twice the static displacement, as you can see, this is almost twice the static stress that you would be getting. So that shows sometimes depending again on the R ratio and the damping ratio, dynamic stress can be much more severe than the static stress. So I thought just throw in a little problem like this, which has at least shows some application. Any questions? Okay. I'm sure you raised this question that am I expected to remember everything from the strength of material? No. All you need to know, just the basic concept that since you were able to, right, you were able to replace any system, right, with an equivalent system, right, single meter frequency system. This K is the stiffness of this guy, right? So that's K. So the force in the spring, which is K times U, this force is the force that causes deformation in the direction that basically this spring is resisting it. In the case of the beam, this is the force. And this, although this is perpendicular physically or geometrically, you think this is perpendicular to it, but that's actually what is resisting it. So the force represents the shear in the beam. So always remember that this is really the shear force. If you have the shear, then you can find the moment and find the bending stress. So no questions? Okay, so let us continue with some more fun, which is the application, further applications of harmonically excited system. Damped or vibration damped system subjected to harmonic loads. As I said before, this topic, forced vibration of damped systems under harmonic load, is important, and so we see several applications, and also it's really the foundation for the rest of what we are going to do, including, believe it or not, for the periodic forces, general forces, and so on. As we have seen by now, we have introduced some really important topics, frequency response function, which is probably the most important one when it comes to understanding mechanical vibration. So I'm going to discuss two other topics that are sort of the result of this harmonically excited damped system. They're independent, you can think of it independent topics, but they're really a sort of a subset of this topic. What do I mean by that? Subset, meaning that, okay, the first topic we want to look at is rotating unbalance. Rotating unbalance in a damped system is really one of the special cases of harmonically excited mechanical systems. It's a very important, as you can imagine, this is a case that is very important, as you will see that, of course, the ramification of an unbalance and what it means physically. But this is a situation that you come across quite often. Any system you can imagine that is subjected to some kind of a harmonic excitation, whether the engine of the car, or a jet engine, or a rotating machinery, okay? We don't have such a thing as perfect world. When you have a rotating system, as we will see, the center of mass and the center of rotation do not necessarily coincide. In fact, probably the most recent case was the blow up of that engine, of that 737. One of the blade breaks is not the problem with the breakage of one turbine blade. I mean, who cares about the turbine blade? What it causes actually is causing such a huge rotating imbalance, as we will see, it leads to failure. So that's the kind of things that we want to study about rotating unbalance and what it is. So this is basically what rotating unbalance is. Let's say you have some kind of a support structure. This support structure can be of any shape, not necessarily a simply supported beam. Can be a, for instance, cantilever beam, okay? In fact, again, my favorite is wing of an airplane, right? You have basically a huge rotating machinery here, jet engine, that is supported by this beam. So that's what we're going to look at. Let's say this little beam is, okay, holding a machinery, okay, that has a rotating component. Again, that jet engine is a good example. It's the casing of the engine and the turbine system which resides inside it, okay? So this thing, let's say, is operating at a frequency omega, this rotating piece, okay? But somehow there is an unbalance. In other words, what unbalance means is that you have this little guy, okay, with some mass, which I call that mass, eccentric mass. That's what E stands for, basically a mass, that somehow has caused that center of rotation is not coinciding with the center of mass. Because you have a little guy that is really disturbing the whole distribution of the mass, okay? So the total mass of this piece of the machine, because it includes that, right? The remaining mass is M minus ME. So maybe I should actually write these down. And why do I call this E? Let's blow it up, okay? Let's say this is the rotating part, so you have this little E, which is the mass of E. This is the distance from the center of rotation to this little guy, okay? And this is rotating like this. As a result of this rotation, obviously, this is a harmonic forcing function. If it's just rotating without this, you have basically a harmonic forcing function, right? It causes, obviously, a displacement of this beam, right? So this beam can be modeled, right, as we've seen it by now, as just something like this, right? So K represents the stiffness of this beam, right? And this is given, assuming that we know what the damping ratio is. So that's what you have, which is going up and down. Let me enlarge that though, because we do need that, okay? So this is what we have here. So this is the mass sitting, and I'm assuming that the beam itself is massless compared with this piece of machinery that is sitting on it. So you have something like this, supported, this is the beam. Basically, these two, if the beam is massless, right, these two basically represent that beam, right? Because it's just a stiffness and a damping ratio, okay? So the beam is going up and down, so I would call the displacement of that, and I'm going to measure it, let's say with respect to here, okay? So let's say if this is the center of rotation, with respect to that, I'm going to measure the displacement of the beam. So U of t is for the whole system going up and down, right? But as the system is going up and down, this little guy, M sub E, is also rotating. So in other words, if you project, if this is rotating at a circular velocity or the frequency omega, right? Or omega t, right? At any point, this is with respect to here, is experiencing a displacement, which I would call that, okay? In other words, let's actually be show it more meaningful way. So what I would do, I would show it like this. Let's say this is going up and down, so you have something like this, okay? So this is rotated, okay? So, in other words, with respect to, so I should have done a better job here. Okay, say this is here, okay? So, and this is here, okay? So with respect to this point, okay, I will, okay, and therefore, this would be something like this, whatever, okay? So, in other words, from here to here, this I call that U, which is for the system itself, has, you know, the O has gone from here to here, right? And this other guy, it has basically gone this distance, right? This is, how do I call it? This is E sine omega t, right? Because if this is omega t, so this, with respect to the vertical line, that particle which was here has traveled here, so projection along this line would be E sine omega t, okay? So what do we have here? So if you want to set up the free body diagram of this and write the equation of motion, what do I have? I have basically this, if this is the mass, and this is the rotating piece, okay? I have, this is moving upward, so we have this, the lumbar force for the mass of the system, okay? This guy is moving U plus ET. So, in other words, this M sub E is also subjected to some inertial force as a result of its displacement. In other words, E experiences what? Experiences a displacement which would be U plus project this E sine omega t, right? So the inertial force that this will be subjected to, which subjects basically everything to this, would be M sub E times the second derivative with respect to t of M sub E, okay, I'm sorry, U plus E sine omega t. So that's the inertial force. Then you have, of course, this f of k, which would be simply k times u. And then you have this f sub c, which would be simply c times u dot. So that's the free body diagram, okay? So if this is the free body diagram, we can simply write, oh, that's good, we have time, okay? So we can just write the equation of motion, right? If you do that, okay, you have, this is the M. This is M, minus M of E, because I've already included that E part. So that's the mass of the remaining part of the structure. So you have M minus M sub E, U double dot, right? Plus CU dot, plus KU, okay? And that would be what? That would be plus M sub E times second derivative, I write it like this, second derivative of u plus e sine omega t. So if you take the second derivative of that, second derivative of u becomes u dot. Second derivative of this would be, first derivative would be e omega cosine omega t, then minus omega times that. So this becomes what? This will become basically, maybe I would write that down that way. So, oh, I don't want, let's not skip any steps here, because I have mu dot minus me u double dot, right? Okay? You will have plus me u double dot, which cancels out with this one. Then this one would be plus me times, the first derivative is e omega sine omega t, then second derivative, I'm sorry, cosine omega t. The second derivative would be minus e omega squared sine omega t, right? So you have m times minus e omega squared sine omega t is equal to 0. So let's read it. Oh, of course, not like parentheses. Of course, plus cu dot plus ku is equal to 0. So let's simplify that. What you get is mu dot plus cu dot, okay, plus ku is equal to, I need to take this to the other side, m, mass of the unbalance, times e, times omega squared, times sine omega t. This is the equation of motion for the rotating unbalance. Now let's see what we observe here, which is quite interesting. If you look at this equation, what is this? These are constants, right? So if you compare this with f0 sine omega t, what rotating unbalance is a harmonically excited system that the amplitude of the forcing function is this. Or, in contrast to the regular force vibration, harmonically excited system that we saw, the amplitude of the forcing function is dependent on the frequency. Okay? You can, simplify these. Okay? In other words, if I write f0, which is me, right, times e omega squared, right? You see that then the U max for the steady state response is what? F0 over K divided by 1 minus R squared plus 2 zeta R squared, right? That's what the maximum displacement was, right? So if you substitute for this, I will do that. You have me e omega squared divided by k divided by this, okay? I can write this differently. What I can do, I can multiply this by omega, n squared divided by omega n squared. Just multiply it by 1. The reason I do that, because this k, okay, is omega n squared is what? K, the square root of k over m, right? And this is, I'm sorry, it's just k over m. This is k over m. This k and this k cancel out, and I will keep this part, actually. I will keep this part, okay? So you will get something like this. You get m sub e times e times, okay, over m, okay, times r squared divided by this function. Okay. So if now you look at this, compare this with what we had before for the regular harmonically excited system, what do you see here? You see this. You see that for the case of if the forcing function was just simply this, right? The frequency response function, magnitude, right, which is what we had, was this, right? So that was what we had. Now, and of course, obviously, maximum, steady state response was HR times F0 over K, right? But now F0 is that. So in this case, okay, is instead of that we have basically forcing function that we have, or f of t, is m sub e times e, okay, omega squared sine omega t. That's what we had. In other words, this is the f0. What you get, h of r then becomes r squared divided by this, okay? From this relationship, okay? This is the frequency response function in the case of rotating unbalance. Yes?
That equation on sort of bottom right.
This one?
That's supposed to have omega squared over omega squared in it too.
Yeah, the omega over omega and square, I replace it with r, right?
Okay.
Right, that's the ratio. So if you substitute, this omega n squared is k over m, k and k goes, and that's what you get m.
Yeah.
Okay. Now, this function, okay, let's now plot that. Okay. For the first case, this is what we know, this is what we have, right? Because we want to compare these two. So this is what you had for the first case, right? But let's quickly look at this. Under this radical, you have 1 minus r squared to the 2 plus 4 zeta r, okay? You can see that if you plot this, this is what you get. I'm going to just quickly do the plot, but of course we are going to discuss that later, next time. If you plot that, looks quite different, because at r equal to 0, everything is 0, because you have in the numerator you have r. So this is how it goes. Okay. In a nutshell, okay, what you see here is you have something completely different. As R increases, as damping increases, now the peak, first of all, the peak, instead of being to the left of R equal to 1, it is to the right of equal to 1. And as damping increases, in fact, this peak shifts further to the right of R equal to 1 instead of to the left. Not only that, at R going to infinity, you can see that mathematically, you have R squared, take R squared out here, so it's 1 ratio. So the limit approaches 1. In other words, there is no way under rotating unbalance that you can ever get below the maximum static displacement. At the ultimate level, in other words, time infinity, at best, you would approach the static displacement. But we will, certainly look at this much more closely because it's very important to differentiate between these two and their implication. Have a great weekend.